Another extremely important class of chemical reactions are acid-base reactions. These play a very important role throughout chemistry. We use acid-base reactions in one form or another in all three-quarters of general chemistry. They're used frequently in organic chemistry. And acid-base reactions play an extremely prominent and important role in biological function. They play an important role in geological situations. They're just generally a very important class of reactions. So we want to learn how to recognize them and understand some of the features of acid-base reactions. And that's going to be the topic that we cover in the third section of Chapter 4. One way we classify acids is according to whether they are strong or weak electrolytes. So we know that acids are always electrolytes because by definition they release hydrogen ion in solution. That is what makes them an acid. So we define a strong acid as an acid that dissociates into ions 100% in solution. It's a strong electrolyte. And a weak acid is simply an acid that is a weak electrolyte, or easier to think about perhaps, it's any acid that isn't strong but is still an acid. So I have some examples of strong and weak acids. As examples of strong acids, we have hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, nitric acid, and sulfuric acid. And as examples of weak acids, acids that do not dissociate 100% in solution, hydrofluoric acid. Notice that this is also a hydrogen halogen acid, but unlike those of chlorine, bromine, and iodine, it's a weak acid. Hydrocyanic acid, acetic acid, phosphoric acid, hypochlorous acid, and many, many more. So a natural question that arises is, how can you tell which acids are strong and which are weak? And we'll see later why this is a very important thing to be able to tell, to recognize acids as strong or weak. And for the purposes of Chemistry 171, at least, I have a very simple answer for this. Memorize this list of strong acids that I'm now highlighting in red. There's 7 common strong acids, and I want you to just memorize this list. I'm very likely to ask you about strong acids versus weak acids on a test, and this is how you know. Memorize the list of 7. Any acid that's not on this list, you can assume is going to be a weak acid. Another way in which we can classify acids is by how many acidic hydrogens they contain in their formula. So for example, we have what we will refer to as monoprotic acids, which simply means there's one H in the front part of the formula. Diprotic refers to acids with 2 hydrogens, and you can always tell from how the formula is written that there's 2 acidic acids. Triprotic acids have 3 acidic acids. Again, just look at the subscript on the H in the front part of the formula. We very commonly refer to di- and triprotic acids collectively as polyprotic acids, simply meaning they have more than one acidic hydrogen or proton. Remember, H plus is just a proton, hence polyprotic, diprotic, triprotic. And you'll never have to worry about tetraprotic. These 3 are really the only 3 numbers of acidic hydrogens that you're ever going to encounter. As a special case, let's look at sulfuric acid. When it releases its first hydrogen ion, that acts as a strong acid. That's a 100% dissociation. But when releasing its second proton into solution, this forms what we call an equilibrium. It only partially dissociates, so that second proton is weak. So the first proton is strong, the second is weak. For bases, we define strong bases slightly differently than the way we define strong acids. A base is considered strong if it is a strong electrolyte and it is soluble. That is, if not enough of the base dissolves in solution, it can't really act like a strong base. So the rule is fairly simple. Hydroxides of alkali metals, we know those are all soluble from our solubility rules. And the heavy alkaline earth metals, we know those are soluble from our solubility rules. Those are strong bases. Remember, the solubility rule for hydroxide says that most hydroxides are insoluble except for the salts or the compounds of alkali metals and the heavy alkaline earths. So if I were to outline these on this periodic table, hydroxides of these elements and of those elements those constitute the strong bases. Putting this information together with acids and bases, we can work out the generic form of a reaction between an acid and a base. Now, I gave you a list of acids, bases, and salts when we were talking about electrolytes in section 1 of this chapter, and this is the exact list that I gave you. But I built this list with a specific idea in mind. That is, if you take nitric acid, this first acid, react it with potassium hydroxide, you form the salt potassium nitrate. The potassium comes from the potassium hydroxide, the nitrate from the nitric acid, and so on. Each of these columns constitutes an acid-base reaction. So our generic typical acid-base reaction is always of the form an acid reacts with a base to produce a salt and water, and you can always figure out what the salt is by combining the cation from the base with the anion from the acid. So here's an example. Hydrocyanic acid reacts with calcium hydroxide. Notice that this is this column of examples. Hydrocyanic acid reacts with calcium hydroxide, produce the salt, calcium cyanide, and water. And then, of course, we have to balance it with the correct stoichiometric factors to make sure that we conserve mass. But the idea is still acid plus base produces a salt and water. And we sometimes refer to this sort of reaction as an acid-base neutralization reaction. We're effectively canceling out the acidity of the acid with the basicity of the base, hence neutralization. In the special case of a neutralization reaction involving both a strong acid and a strong base, we have a special situation. We can represent that with a molecular equation, much as we define molecular equations for metathesis reactions. But in this special case, we can also represent it with an ionic equation. And the reason that we can do this is because these ions are formed since we know that HCl is strong. If it weren't a strong acid, it would not be breaking apart completely into ions, and so we couldn't represent it as existing as ions in solution. This is a special case for when the acid is strong, in which case we see that the net ionic equation for a strong acid, strong base neutralization, if we cancel out all of the spectator ions, the barium appears on both sides, what we end up with is hydrogen ion reacts with hydroxide ion to form water. That's really the essence of an acid-base reaction. Finally, acid-base reactions have some properties that make them extremely useful for measuring things, as we'll explain in one of our later sections. And that is, acid-base reactions are always very quick, and they react completely if one of the reagents is strong. That is, what all that means is either the base is a strong base or the acid is a strong acid, or both. But if at least one of them is a strong substance, then we guarantee that the reaction is complete. And that tells us that once we stir all of the reactants together, we can reasonably assume that they have reacted, because it's a rapid reaction, and that they have reacted stoichiometrically, because the reaction is always complete for a reaction with a strong acid or a strong base.